Okay, it's about time, so let me get started. Hello everybody, this is Junichiro Horikawa, and this is the weekly tutorial live for Houdini that I'm doing recently. And bi-weekly basis I'm going to teach you some stuff that I made, stuff that I found interested using Houdini, plus some basic codings. Okay, and the topic today is to create a spiral-like surface, waving surface on any given geometry, like box, sphere, could be a plane, torus, or any kind of geometry you would like to use. And the uniqueness of this method is to use the mesh face itself to extrude it based on a wave function that we're going to create together with some timeline frame values to make an animation like this. And there are some parameters you can set, and something like the number of waves, height of the wave, and a number of spiral waves right here. Like if you have multiple spiral waves, you have kind of a windmill-like pattern like this. Right? So the function itself is pretty easy, but in order to implement it in 3D, you need to think about a little bit of vector operations rather than doing on a plane. Doing on plane is pretty easy, so I will start by explaining how to do that in plane and extend that to a 3D later on. And you could also use a remeshed geometry like this one as well. And if you want, you currently this works on primitive faces, but it could also work on each point to make a more smooth surface. So if you want that, you can just change some of the code to make it work on points as well. So if you want to know that, let me just know. All right, so let me get started. I'm gonna move the... Okay, then the file that I have just shown could be downloaded from the video description page on YouTube. So if you're interested seeing how it works by looking at the code, then just download the file from the page. Yeah, anybody can download it. Alright, so let me get started. I'm going to create by making a geometry first, as always. Then I'm gonna start by creating a grid to make a simple spiral wave animations on a grid. Right, and to make it, and I want to make it work on each grid surfaces or grid face, this squares. So let me set some resolutions for this grid, like 30 by 30 or something. Right, you could, maybe you can parameterize this if you want. I'm just gonna leave it as this for now. Okay, the next thing I would like to do is to set the starting point of the spiral. So before getting into the real coding, let me explain the process, what I would like to do. Okay, so say you have a geometry like this, like a plane, and the first thing you want to set is the starting point somewhere on the plane. And what you want to do, what you want to make after that is to create a spiral wave like this. And based on the position of this spiral line or spiral curve, you want to make a mountain like this. So when there's a spiral curve, you have a high mountain. If there's no curve, the the the, the value in between those two curves should be a valley, and so on. And the characteristic of this spiral wave can be decomposed into a really simple composition of sine waves, hopefully. So first thing I would like to do is to make a really simple sine wave starting from this point to a multi-direction, omnidirection. Meaning from here I'm going to make a spiral wave, sine wave like this to every direction like this. But if you have a curve like this and say these are the mountain points, then what you get is more like a ripple-like effect. But in order to make it like a spiral, what you could do is to offset each sine wave starting angle. So every sine wave right here drawn here starts from 0 degrees. But what if this one starts from 0, but if this one starts from 90 degrees, and this one starts from 180 degrees, and this one starts from 20 to 70 degrees, then you have some offset to the wave. So the first wave should be like this, the second wave should be like this, and the third wave should be, okay, it's out of the third wave should be like this, and fourth wave should be something like this. So by offsetting the starting angle, you can kind of control the starting height of each sine waves, and by having those offsetted sine wave on every step, every like some step in 360 degrees, then you'll probably be able to get a spiral wave. So that's the method that I'm going to follow. Alright, so let's try to do that. Okay, so first of all we need some starting point, and since I am going to work on a primitive, I'm going to change the height of the primitive. Let's find out the starting primitive value, or starting primitive face. And you can choose it randomly, or you can you can choose it manually by having some guide points. So I'm going to create a guide point in this case. I'm going to use add node to add 1 point on a space and move that point so that I can use this as a starting point. Now what I want is a primitive number which is close to this point. So in this case, this primitive face. So let's find that out by using some simple script, using primitive wrangle, or maybe detail wrangle. I'm gonna change it to detail since there's only one primitive face that you want to find out. Okay, and I'm going to retrieve the number of this, the index number of this primitive, then store it in detail attribute. Okay, I'm also going to show the geometry spreadsheet so that I can check the attribute. Alright, now let's connect this add node as a guide point, which is this point that I've created. Let me visualize this point a little bit bigger. Okay, like this. Okay, I'm gonna set it to the second input of this detail wrangle. I'm gonna say start prim index. Then I'm gonna connect the grid that I want to convert it into a spiral wave into a first input of this detail wrangle. Then let's write some code in order to find out the point, the closest point on a primitive. So first of all, I'm going to get the point position from the second input using point 1. It's point 1 from second input. The attribute name is p. Since there's only one point, I'm inserting 0 as an index number. Right, then in order to get the closest primitive number, the function that I'm going to use now is this xyz distance, which can retrieve the closest primitive point based on the searching point. Okay, so I'm going to search on the grid, which is from this first input, then use the position that I got from the second input as a searching criteria. Then I need to have two variables. One is primitive number and one is uv as a output value, which is being updated with this function. So right, like this. Then after activating this code, activating this function, you will have a primitive number and uv updated by this function. So you'll get the closest primitive number from the point that I used as a guide right here. And let's see if that's true. I am going to store that as a detail attribute named as sprim, meaning as starting prim. Okay, let's see. Let's look at the geometry spreadsheet to the detail, and I have number 661,661. And let's check that out if the number seems to be correct. So I have just turned on the primitive number display. Then let's get it. We cannot really see the text. Let's scale up the font. Oops, not this one. Was it where's it? I think it was a guide. Oh yeah, this one. Make it large. Okay, and the number that I am looking is 661, so this one. And let's also look at the points, which should be a guide points. This one here, right here. And seems like it's correct. So the point was around here, and the primitive number that I got is this one, so it's correct. Oh, hello Sal. Thank you very much for the super chat. Appreciate that. Okay, so now I have got the starting point starting primitive number. Let's get to the next step. So the next step that I want to do is to first of all create a normal vector for each primitive face. Well, currently since this is a grid, flat grid, so all the normal vectors should be upward, meaning y plus y vectors. But since we want to use this, you want to change this geometry later on to more three-dimensional geometry rather than grid. So even though this is plane right now, I'm still going to calculate the face normal, primitive normal. So I have just attached a normal node, and I'm going to convert this into a primitive. So that as a result, you should be able to get a upward vector, a normal vector for each faces like this. And if you look at the primitive attribute, you should be able to see a new attribute called n. Okay, we will use this later on. Right, now next thing I would like to do is to create a circular sine wave from a starting point that we have picked up. So that means, let me delete this. So in order to create initial sine wave from a starting point, so for example right here, what you need to know is a distance between this point and each other point on a grid. So this will always be the base point, and what you need is the distance for each point on each other point. Now that is used as an angle in order to create a sine wave. Right? So that's the first step, and then you also need to get another attribute or values using the center point in order to make a spiral, in order to make a shift offset, in order to make an offset for the sine wave. So to make an offset, think about that this is a 2D geometry. Well, it looks like a 2D geometry right now, but it could happen that this will be a 3D geometry. But for now, think that this is a 2D geometry, and think that there is a axis on this plane. And this axis, say this axis X and this axis is Y, right? And based on the X-axis, for each point on a plane like this, you want to calculate the angle based on this X-axis. So for this point, this will be like 45 degrees. For this point, this will be 30 degrees, and this point, this will be close to 45 as well. This point, something like 120 degrees, and so on. So for each point on a grid, you want to find out the angle value based on the center point that you have right here. And we're gonna use that, we're gonna use this angle value as a shifting value in order to make a shift to a sine wave to actually create a spiral wave. So that's the two values that we want to create, or we want to retrieve out of this center point. So let's do that. So first we're gonna do with the simpler one, making calculating the distance between 2 points. And I would like to create an attribute for each primitive, so I'm going to use a primitive wrangle. And let's say dist and angle. Right, let's open up the code editor. Okay, first of all, let's calculate the distance. So the first thing I would like to do is to get the starting point or starting primitive face, and you can retrieve that by accessing to a detail attribute called sprim, which was the index number of the starting primitive. So you can retrieve that by accessing to a detail, which is stored as sprim, I think. Let's check that. Go to a geometry spreadsheet and go to detail. You have this sprim attributes on a detail. So what I have retrieved right now is this number 661, and that is the primitive number that I want to use it as a starting primitive. Okay, and from this primitive ID, I would like to get the actual position of the center point of this face. So by accessing to a prim attribute called P, which is hidden, but it's actually a center point, a centroid of the face, at sprim, you could get the center point, vector position. Then you might also want to get the vector value, I mean the normal vector of at sprim position. So vector I'm gonna name this as norm, like this. Okay, and in order to calculate the distance, which will be simple, you just need to calculate the distance between the current primitive position, which is at P inside a primitive wrangle, means the center of each primitive face, right? And then you want to calculate the distance between this starting primitive, like this, right? So if this face is the starting primitive, then what you are calculating for each primitive is the distance between this center point to each of the primitive center point, and store that distance inside each primitive attribute. So I'm gonna create a attribute called distance, and then store what I have just calculated. Okay, let's check that out. Going to the primitive attribute on the geometry spreadsheet, and there you go. This is the list of distance, and we're gonna use this later on as a angle value in order to use it with a sine function. Okay, now next we're going to create a angle value on each primitive face in order to use it for shifting the sine wave in order to create a spiral wave. So let's name this angle shift angle. Okay, so in order to calculate the angle for each point or each primitive, let me explain it how you could do that. So first of all, you have this main point, which is the starting primitive points, right? And there's also a point that you want to refer to somewhere around here, say. And say you already have some base angle like x-axis, base direction like x-axis. And what you want to get is the angle of this value, from this point to this point and this point to x-axis. So how do you do that? Well, if this is the vector A and this is vector V, and in order to do that, you can first of all create a to B vector by calculating B minus A, and then you can use a function like a10(2), which is often used to calculate retrieve the angle from a vector value. So by using a10(2), you have two parameters, y and x. So inputting y and x value of this vector will give you an angle, this one, as a radians value. So let's do that. Let's try to retrieve that value. Okay, so first of all, I'm going to create a directional vector named as dir. Then subdivide P at P, which is the current primitive position, by starting position, right? Then I'm gonna normalize this just in case, so that the length will be 1, equal to 1. Right, now let's try to calculate the angle from this one. So as I said, you can calculate the angle using, let's name this tang or ang. You can use a10(2), and as you see, you have two parameters to input. One is their y, and one is their x. Okay, as a result, you should be able to get the one that you will need to use as a shift angle. So I'm gonna name the attribute named as t-ang, then update the t-ang with the one that I have just calculated. Okay, let's check that out. Okay, so I have the value like named as tang. Okay, I think something is wrong. Okay, I know why. That is because I have used the dir.y, but actually you cannot use y because this is actually on a xz plane, so you gotta use z value instead of y. Right, let's check that out. Okay, so I have angle value in between minus 3 point something to plus 3 point something, so it's around from minus pi to pi, I guess. So let's check those colors by coloring each faces using that value, using that tang value, the angle value. I'm gonna use the color value. This is just the debug what kind of values that we have retrieved. So I'm going to change the color type to primitive, and I mean the class to primitive, and then change the ram from attribute. The attribute name is tang, and the range is from minus pi to pi. Okay, now I don't see any changes. Let's go back to okay, so I think you see some changes right here. Let's say that the minus pi value is equal to blue and plus pi value is equal to red. So this value indicates, this color indicates which primitive is equal to which angle, right? So if I change the position of this base starting point right here, you see that the angle changes corresponds to the position of starting point position, but always the angle of 0 is equal to right here. And since when you use sine wave or cosine functions or trigonometry functions, angle 0 and angle 360 degrees is equal. So you see that the red one and blue one should always be the same. Should always give you the same results. So to make it more easy to understand, you can set the same color for the starting point and the end point. Then this will be more understandable. So this is the angle. This is where the angle is close to 0. This is the angle that is close to 180 degrees. Right. So I think the angle that we have retrieved seems good. But the problem is that this method only works on a grid, plane surface. When it comes to work on like a curved surface like spheres or torus or any other kind of geometry other than plane, then you cannot really retrieve the angle in this way. So to make this function more flexible, which should work in order this to be work on any kind of surface, you need to think about how you could do that. So let's input some other kind of geometry like sphere, or maybe sphere. It's fine. Okay, and let's change this shape to polygon, and let's give the size close to the grid, so something around here, like 5. Maybe that's too big. 3. And let's give a lot of faces by changing frequency. Right, So let's connect this instead of a grid. Then as a result, you see something weird right here, weird result like this. So if you try to move the point position like this, you see the result doesn't really look correct. All right. I want some maybe this part to be more bluish, this part to be more reddish, but I see some weird line like this. Doesn't really seems correct. The color distribution doesn't really seems to be correct. So in order to fix that, you need to think about how you can retrieve that value instead of working on based on the flat plane. So when you have a curved surface like this, what you need to have is first a normal vector of that curved surface, if this is the point that you want to check, right? Or maybe yeah, if this is the point that you want to check, right? And then say this is the starting point. Okay, then you can, what you can do is to first, well, this might be a bit of hacky way to do that, but what you actually want is the angle on top of this surface. Maybe say if this is the angle 0, then this should be angle 180, and this angle should be 90 degrees, and on the back side the angle should be equal to 270 degrees. And it's hard to retrieve that value based on this information right here, but by doing some simple operations to this whole stuff, it becomes a bit easier. It becomes close to what it looks like on a grid. That is to first of all create a rotational matrix in order to convert this normal vector to sit on a plane, xz plane. So this normal plane will be equal to y. So first of all, create a rotational vector so that n becomes 0, 1, 0 vector, right? And after you have retrieved that, what you can do is get the perpendicular vectors corresponds to this normal vector for each point on a surface. Like for example, if this is the point that you want to look at, that you want to check the angle, first thing you want to do is to get the perpendicular vector between these two vectors, which can be calculated using a cross function, cross product. So by having two vectors, you'll be able to get a perpendicular to this plane vectors. And as a result, say this is the normal vector, right? And this is the original point position. And as a result, you have this set of directional vector. One is normal vectors and one is a vector which is lying on top of the tangent vector of this surface, and which is equal to 90 degrees to this normal vectors. After we have retrieved that, we can also rotate this tangent vector using a rotational matrix, and as a result you should be able to get a vector that is lying on the xz plane, right? Say, let's name this deer. And now you have two vectors. You can actually, and the direction that I do have just remapped or rotated is actually on the xz plane, so you can just use the same function a10 like we did before in order to calculate the angle, cosative angle. So that's one of the way you could do in order to calculate the angle on a 3D surface. Okay, and okay, Sal gave us another solutions right here, a cos using dot v-app. Maybe this is more smart. Yeah, I guess that's more smart. The way that I'm doing a bit hacky using Houdini functions in order to retrieve that to make it more understandable. So if you have more mathematical knowledge, I think the one that Sal is writing is better, I guess. Right. Okay, but let me do in my way in this case to try. Right, so currently I have normalized vector right here, and first of all I would like to make a rotational matrix so that in order to the one that I want to rotate is the normal vector that I got here for each primitive faces. So I want to create a rotational matrix so that I can move this normal vector to up vector, which means 0, 1, 0. So what I'm going to use is matrix 3 rotmat. This is a rotational matrix, and I'm going to use a dihedral function which can create a rotational matrix that rotates one vector to another vector. So what I want to make is to rotate a normal vector into a y vector like this. Right. Now after making this rotational matrix, we don't next thing I would like to create is a cross product, calculate a cross product between the current normal vector, which is equal to these lines on a sphere, and the direction from current point to starting point, this one, to actually get the tangent vector at the starting point. So okay, like this. So let's visualize this if I really got the information that I want by using by calculating like this. So I'm going to set it as a cross. Then let's try to see how it looks like. Okay, I think I have some spell mistake. I'm going to add a marker for a vector like cross, use vector, Okay, and the attribute name is cross. The length is a bit too... Okay, now if I show up the normal vector as well, you see that all the yellow vector, which should be a cross vector, is all tangent to its surface laying on, or face, the primitive face laying on. So I think this is correct. And what I would like to get is the actual angle of each this yellow vectors, and I can do that by remapping this value into xy plane first using this rotational matrix, then do the calculations. Do the same calculations that I did using A102 right here. Okay, it's a bit too long way to write up, but to make it well, for myself it was more easy to understand. Right, so let's do that. In order to rotate the vector, which is this one that I want to rotate, you can multiply equal using the rotation matrix that you have created right here. Okay. Okay, and as a result, the cross-directional vector should be lying on the XZ plane. If you want to check that, you can still have a cross direction viewed as a marker. Okay, so if you look at each yellow line, each yellow vector that has been rotated, you can see that currently each line is actually lying on XZ plane. It's a bit hard to see since this is on a 3D surface, but you see that all the curves are actually on top of XZ plane. So meaning y value for this vector is equal to 0. Yeah, can also be checked at here. Well, it is not exactly 0, but it's really close to 0 if you look at the value right here, because it's e minus 8 or something. So so far so good, I think. What you need to do next is to just replace this direction with cross direction right here. Okay, to calculate the angle. And let's see the result by checking the color again. Now the color seems became a bit more gradient. If this is the point position, which should be close to the starting point, which should determine the starting point. So if I move this, you see that the angle distribution becomes more clear. You can clearly see that the left hand side and right hand side has some evenly distributed colors, meaning you have angle between 0 to 360 degrees distributed evenly. Okay. Thank you very much, OC for the super chat. I appreciate that. Thank you very much. Okay, so now we have got the angle distribution. It's time to use those values, both distance and angle, in order to view it as fractal, not the fractal, the spiral wave, right? So let's do that. Going back to the primitive wrangle, and currently if you look at the primitive attribute, you have distance and angle right here. I know the angles range is in between minus pi to pi, but the distance is going to change based on the size of the input geometry. So I would like to get the maximum value of this distance attribute so that I can use like function like fit, so that in order to control the range. So I'm going to use the attribute promote, and then set primitive for original class, and the original attribute name is equal to, what was it, dist. Then I'm going to make a new class on detail named as distMax to store the maximum value of the distance attribute. Okay, let's check that out. Going to the geometry spreadsheet, to the detail, I have currently the maximum distance value stored in a detail attribute. Okay, and I'm going to use this later on. Now, next thing I want to do is to actually extrude each primitive face in order to create a spiral-like wave together with the animations. And in order to extrude each faces, what I need is a normal direction for each point rather than each primitive, because I want to make each faces stick together rather than having a gap in between the extruded geometries. So to do that, what I want to do is to extrude each point based on each point normal direction. Alright, so I'm going to create another normal attribute, a normal node with a point option. Oh, hello Pavel Varishnikov. Thank you very much. Thank you very much for the super chat. Appreciate that. Thank you very much. Alright, so let's check out the point attribute, and you see that there's a new normal attribute has been created, but instead the primitive normal has been disappeared by using this one. So that's why I needed to create this later after I have retrieved the angle value right here. Okay, so next I'm going to use another primitive wrangle to extrude each faces based on the distance value together with the angle value that we have calculated right here to create a spiral wave. Okay, let's name this spiral extrusion. Okay, so I'm going to open up the code editor. And first thing I want to do is let's change the shape to a flat geometry to make it easy to see what's going to happen. So okay, first of all, I'm going to retrieve the distance attribute from a distance attribute named as dist, and let's also get the max distance value from a detail that we have stored using attribute promote, like this. And let's also get the the angle value as well, from a angle attribute that was named as t-ang, I think. Okay, so these are the three values that we want to import from an attribute value. Let's check that: dist, tang, and detail distmax. Okay, looks good. Right, so first of all, let's create a simple sine wave using a distance value right here as an angle. So I'm going to make an angle value using a distance using fit function to remap this value, which is from 0 to dist max, and I'm going to remap to from 0 to probably some angle value pi multiply by some maybe some parameter values. I'm gonna name this as wave num. Doesn't have to be integer, this one, because it's going outward from the center, so doesn't really have to be repeatable. Okay, so it should be okay. Apply, and let's check the code, and let's promote the parameter like this one. So you have the value from 0 to 1 right now. Maybe that's too small because 1 will just give you 180 degrees. That doesn't give you much number of waves. So let's change the range from 0 to 10. Right, and let's use this as a height value in order to change the height of each primitive face. So to do that, I'm going to create a value called height, and let's first calculate the sine wave using a wave ang. It's this one. And since using a sine wave will give you a value in between -1 to 1, you can use a fit function to remap into a value range that you want to use. And in this case, probably from 0 to some maximum wave height that you specify yourself. Alright, so let's check that out. Okay, now you have two parameters, and currently you don't see any changes on the geometry because I haven't really modified yet. So in order to modify this geometry, I need to use this height value in order to change the height of each primitive face. So let's do that. And to do that, one way, well, since we want to extrude the face, extrude each faces, in order to do that, what you can do is to retrieve the point position for each faces and create a new point on top of that face using this height, moving to the normal direction for each point. Then create the side plane based on the height as well, height value as well. But for now, to make it simple, in order to debug if it looks correct, first thing I would like to do is to, since all the plane, I think each faces share the points, the neighbored points right here, meaning all the points are welded. So let's make all the points unweld by using some component like facet, and click this unique points option so that you have points that is unique to each others. No weld vertices exist anymore. Every point is unique, meaning after you have unwelded, the point number becomes from 900 to 3364. So that is because all the points has been unique. No sharing between multiple faces exists anymore. So that's the reason. But by doing it, you can move each faces independently. So that's kind of a good for this kind of geometry. So that way you're going to create. So let's do that way. Alright, so in order to move each point for each faces, first of all, let's retrieve the point list for each faces using prim points. this. And since this is a square face, you should be able to get 4 points, but if it's triangle, you should be able to get 3 points. So loop through all the points on a PTS list. And first of all, retrieve the point position for each point using point function PTS at I index. Alright. Now what you want to do is to move this point upward or to the normal direction using this height value right here. So you could also retrieve the normal value from each point like this, and then create a new position using a current point position plus a normal direction multiplied by height. Right? Apply, and then finally reset or set the point position. Reset the point position with this newly created point value. So set point attrib at PTSI with this new position. Let's see. Right, something happened. Each face has been moved upward using a function that I have using the height value that I have created right here. Okay, if I change the number of waves, it does seems to change the number of waves corresponds to this value, and also the height, the maximum height also changing. So that seems good. That seems good. And let's also try to see this if this works on a sphere as well. So let's reconnect this on a sphere. It seems like this still works for sphere as well. Looks good. Right. Now, since this seems to be good, next thing that I want to do is to create the side face for each top faces to make it look like a solid geometry. Well, it's not actually going to be a solid geometry, but make it look like a solid geometry. I want to create the side faces as well. So let's do that. And in order to do that, let's go back to the code editor. Now we already have the point at the top part, but in order to create a side faces, you also need the point on the bottom part, which is actually equal to this PTS one, but I could actually create a new points using this original point position. Right? So let's create a bottom PTS list with the empty array. Right? And I'm going to create a new point and store that point number into this list and use it as a bottom point list. And this will be the top point list, actually. And use those two lists, we're going to create a side faces. Okay. Okay, I have a comment saying, can we use poly extrude instead and map distance attribute? Oh, I don't know if I didn't know if you could do that. Let me check. Poly extrude. Let's do that. If that's possible, that will be much better. Okay, let's see. Let's try this out. So I'm going to set it as, well, I think not. Okay, let me just close this for now. And okay, what am I? Well, I think I have some cache being left over right here. How do I delete this? Sometimes it happens. Okay, it gets being deleted. Okay, well, is there any way I could use an attribute in order to control the height of each extrusion? I'm not really sure if you could do that. Is this one? Distance scale. Ah, maybe this one. Let me see if I could do this. So let's make the distance to 1, and then the Z scale to height. Okay, no, doesn't work. Okay, I am not sure if this works. Oh yeah, I think I didn't have a distance. Height. Let's change to this. Okay, well, seems to work, but the problem is that, as you can see, there's a gap in between those two neighbored extrusions, so that's not what I really want. I want to use the point normal to, but what if I choose this one? Oh, okay, well, this does really work. Okay, I think this is much better. This is much easier to do this, so let's just do it in this way without using this value, this extrusion. So instead of you create an extrusion inside a vex, I'm going to just calculate the height value inside this vex. Use that height attribute, new created height attribute for a poly extrude. That might be much smarter in Houdini way. Okay, so I'm gonna delete that, and I'm going to store this height value to height attribute, then use a distance scale, the height. Okay, and let's normalize the vectors. Okay, it looks good. Yeah, it's working pretty well, I think. Alright, so let's calculate the height value, calculate the height value, and forget about making a poly extrusion functions in Vex. Right, thank you for that. Didn't really know about that. Alright, so currently we have this wave function which works on a surface like this. Now next thing what we want to do is to create I use the tang value right here in order to shift this wave at each angle using an angle value to make like a spiral wave. So to do that, we are going to, what we could do is to where can we use that? We can use this T-ang in order to modify this wave ang used for a sine wave. So by adding, simply adding tang like here, like this, actually you can simply create a one continuous spiral wave like this. Actually, to make it more customizable per metric, you can, what you can do next is to multiply this tang that you have imported with an integer value, which should create a multiple number of the range in between 0 to 360 degrees. Since this tang value is in between minus 180 degrees to plus 180 degrees, which corresponds to 0 to 360 degrees. You can, by multiplying by integer value, you can remap that into 0 to 77 to 20 or so on, the multiple number of 360 degrees to make the spiral continuous. So let's name this, let's name the parameter spiral num. Alright, so if it's 0, you have no spiral wave. If you have 1, you have one spiral wave. It's a bit hard to see. Let's make the height value bigger. If you make it 2, you have 2 spiral wave, 1 here and 1 here. It's really hard to see here. Let's make this resolution a bit higher, like 20 for now. Okay. So far it's working okay. Now next thing I want to do is to make an animation so that the spiral wave seems like it's rotating counterclockwise or clockwise. So to do that, it's pretty simple. You just need to add some additional angle value to this wave angle using some frame related values. So I am going to first retrieve the frame value. The current frame value will be this value right here. So I'm gonna retrieve that using global attribute using @frame. And if you want to make a loop, if you want to make a loop between the first frame to the end frame, then you also want to get this end frame value. So I'm going to make a channel first, the parameter channel first, by naming this fend. Accessing to a global variable on top of a parameter expression as a parameter expressions. Then you'll get this value right here, end frame. Then divide this current frame with the f end, will give you a value in between 0 to 1. And I'm going to actually use this f ratio, which is in between 0 to 1, in order to use it as a animation. So I'm going to add an f ratio and multiply it by multiplication of pi, or maybe pi multiplied by 2, I'm not sure. Maybe let's try with this one. So currently I have this value right here. So if the frame is equal to 1, then this value is close to 0. This one goes to 240, which is the end. This value, the @pi, this value will be equal to @pi. I mean the $pi. Well, in that case, maybe it's better to multiply by 2 to make it 360 degrees. Okay, so that the first one and this last frame will link. Okay, now I see some animations, but it's too slow. Let's make it 40. And here you go. I think I see some animations right here, starting to create a spiral-like animations. And if you make it a negative value, the rotational direction becomes the opposite. And if you try to make it like other than 360 degrees, you see that there is a switch when it goes from end frame to first frame. So if you want to make a loopable smooth animations, you want to make the multiplication of 360 degrees. Well, you can also do 4, but it doesn't really make any sense. It just makes it faster, so making it by 2 is fine. Just use this end frame to control the speed. Right, looks good, I think. Now I cannot really see the wave changes if you get close to, because there's not much visual changes except for the extrusions. Well, it is a big change, but I want to add additional like colors based on the height, so that it'll be more easy, it'll be more clear that each the extrusion is different, the height is different, and the spiral should be seen more clearly. Okay, so to do that, well, let me first go to the extrusion, poly extrude, and see if I have the height attribute being preserved, and seems like it has been preserved. I'm not sure if it has been resampled or not. Let me try. So let me try to use this height attribute on a primitive to colorize the value. Okay, so the maximum height is equal to the value, which is right here, wave height right here. So I can copy this parameter, then go to a ramp from attribute, set it as primitive, then set the attribute to height, then set the range from 0 to a parameter that I have set as a wave height. Okay, and if I change the wave height to something different, it still works. Okay, looks good, I think. Now it is working as intended. Right. And if I change the wave num, it still works. Still works. Now maybe I don't really need this face one, and instead I could go back to the poly extrude and set it as individual elements, and this should still work. And this might be faster to calculate. Yeah, I think so. Alright, so this is pretty much it, what I wanted to show you. Pretty simple operations that I done here. You can control the number of waves, you can control height of the wave, number of spirals. Maybe I could add another parameters, like if you want to rotate it on clockwise or counterclockwise, maybe. Let's try to create a toggle. Right here. Named as clockwise. Wiser. Okay, so currently it's rotating clockwise, I guess. So if the toggle is checked, then I want to make it clockwise. If not, then gotta make it negative or counterclockwise. And I want to change this expression right here. So let's say, oh wait, that was negative. So if it's negative, then it should be clockwise. Let's say plus, and I am going to multiply this by this toggle value, and toggle value can be retrieved as an integer. So int clockwise. Okay, and I can make a float value like clock multiplier. first of all, I'm going to subdivide this clockwise value by 0.5 so that if it's 0, if it was 0, meaning if this is turned off, then this calculation will give you a minus 0.5, and if it's positive, then you'll get a positive 0.5, and by multiplying this by 2, you get either -1 or +1. Okay, and I'm going to multiply this with this. Okay, so let's check if the rotational, okay, it's the opposite. So I'm gonna make it negative right here. So currently this is rotating clockwise. If I uncheck this, it's going to rotate counterclockwise. Okay, looks good. Now let's store all those parameters into a null node so that I can store access it later on. Right. Gotta check for a bit. Linking parameter. Go to, well, there are several parameters that I wanna use it. Let's check one by one. This doesn't really have anything. Distance and angle. Do we have anything? Nope. The spiral height. Yes. So first of all, number of waves, wave height, spiral num. I don't really need the f end. And the clockwise toggle right here. Okay. Accept. And let's check this out. If I check clockwise, load's working, wave num, it's working. Okay, wave height's working, spiral num is also working. Now, let's make this low res for now, because it's gonna be more interesting when it becomes low res and if you can see the shapes. Okay, let's try out with the different kind of geometries. We have already tried plane and sphere. Let me try with torus as well. Let's first of all, let's set some number of faces by setting rows and columns like this. Okay, maybe I could do 50 by 100 and see if this works. Okay, alright, maybe the wave height is too much, or maybe I can scale it a better. Right, looks good. Make it 2, and here we go. Let's make the number of spiral 1 and try to move the at this base point position. Let's see if I can change the starting point for the spiral. And indeed it is changing like this. Alright. Okay, I have a comment. Can we try with rubber toy? Yes, of course. Let's try that. Let's try that out. Let's make the scale similar to the other geometry, like this. Probably like this. Okay, let's see how it goes. Okay. Alright. Looks funny. No, it's a bit heavy. Well, cannot really see the spiral itself, maybe due to the detail of this geometry. One thing I noticed is that it becomes a bit slow with this number of geometries, and I guess it's because of using a poly extrude, I think. Let me check the performance. Let's recode, play. Yeah, as I expected, the poly extrude using a lot of CPU calculations. And I think you can kind of fix that by using maybe VEX code. Can we try that? Well, the thing that I wanted to show you is already done. So if you are satisfied with it, you can leave and maybe you rewatch the stuff, or you can download the files. But let me just try out rewriting the extrusion code with the VEX so that to see if the performance will be fixed or not. Oh, thank you very much, KT Ma, for the super chat. Always appreciate it. Okay, so let me write up some code to try the extrusion using the VEX with instead of using poly extrude to see the difference. The visual should be same. I just want to check out the performance. Alright. It's not an easy way to do it, but if you need more performance, that might be a good idea. Okay, so I am going to first access to a list of points. And for each point, I'm going to access to a point index. Also accessing to a point position. Also to a normal direction. Right? And first of all, let's also create a list of points. In this case, I'm just going to create a list of points for the top part. So tpts, I'm gonna name this tpts. Right, and then create a new position called endPos, and at position plus normal multiplied by f height, which is the primitive attribute stored in each primitive. I think I can use this to control the height for extrusion. Right, now I can use a new point. I can create a new point using add point at endPos. Right, and store that endPos into a new tpts using push or append. Like this. Okay, now I do see some list of points right here. Okay, now there is just points right here, but I also need to create a face out of these points, so let's also create a primitive named as poly, and use add vertex for each t-prim with npt. Should create a square face on top, using a height value to move the base surface upward to the normal direction. Right, now the reason why it's black is because the normal value is not applied to each point, so we can fix that later on. Next thing I would like to do is to create a side faces. I can do the same loop for PTS, but this time we're going to use the TPTS as well. inside. And in order to make it faces, there is 4 points, 2 points on the bottom, 2 points on the top. So the first point comes from PTS I, the second point comes from bottom points I plus 1. But if it scores more than length of PTS, I have to reset it to 0. So I'm going to calculate the modulus like this. And then PT3, I can kind of copy this thing. Then instead of using PTS, I can use TPTS, that's the top point list. And for the TP4, I can just say this. Now I can now create a side prim. Let's name this int side prim. Add prim poly. Okay, and add vertex 0 side. Or maybe I can just input those 4 values, 4 points list right here. Okay, do we have created the side faces? I guess so. Gotta check by connecting a normal. And finally, I am going to remove the original primitive because that's the bottom part, which is going to be hidden. We don't really need to show that. We don't really need to have that. Prim num. Okay, now connect the normal. Okay, so the visual looks like this, and let's check the visual with the one output from the poly extrude. Similar, just that the texture has been broken. Well, let's forget about the texture for now. But instead of the textures, the geometry, the extrusion seems similar. Okay, so let's check the performance between two. I'm gonna start with the one that I have created from the poly extrude. Okay, go back to the performance, record, play. I'm gonna play for, okay, let me just go reset to, I'm gonna play until maybe frame 10. Oops, got 11. So 2.5, 2.4 seconds. So, right. Now let's change this to a 1 from a vex. Okay, what's wrong with the color? Okay, I think I'm missing the height attribute on the newly created primitive, so I have to apply a height attribute. Set prim attrib height. Do the same for the top part. Wait, I was missing the primitive index right here. Same for the side primitive. Okay, so let's check this out. Go back to the performance, click let code, and let's see until frame 10. Okay, well, became 13, but I think obviously the calculation seems around 5 times faster than the extrusion. So yeah, using the poly extrude is good because it's pretty simple to use, straightforward to use. You can just adjust the attributes right here, the parameters around here. So I think it always is a good idea to use. But if you need more performance, maybe using Bex might be a good option at some situations. So you might want to check that out. Okay, so let's check the one with the rubber toy, but doesn't really seem like that. I don't really see the spiral. Where is the starting point? Okay, so where is that? This one? Okay, now I see some spiral right here. Interesting. Maybe if I increase the wave. Right. I don't know if I like it, but it looks interesting still. Right. Okay, so that's what I wanted to show you. If you have any questions, I would like to answer it. If not, I would like to end the stream at this point. Thank you always, everybody, for the comment. Really appreciate that. This is really a simple one using with the grid, but the effect is really powerful. Can we use surface dist? Maybe. Let me see. Let me check the vex functions. Probably, yeah, you might be right. Using surface distance might be a good idea for 3D surface. Could be. Okay, let me try that out, if that still works. Maybe we could use this kind of complex geometry like rubber toy, or maybe starting with the torus might be okay. And let's move the starting point to a side, like here. Okay, and where was the... Okay, this was the one that I was calculating the distance. So instead of using just the linear distance function, maybe if I use the surface distance, you might be able to calculate distance between 2 points along the surface, so that might give you a better result. Okay, well, let's try that. The geometry that I want to search is 0 and the point group. What's the parameter? PT, the name of the point group or the pattern to generate a point group. Empty string will just search everything, so let's just search for everything. And the point attribute, let me just show up the help p attribute, the name of the vector attribute to use measure distance between connected points. Using p will give the world distance along the surface, but a custom attribute can be... Okay, well, p is fine. Okay, searching point, the point to measure the distance for... Yes, at p, the current point position. Or, yeah, I think so. Is that so? And the max radius. Wait. Is that what I want? I am not sure. I'm not sure if that. Wait. Does. Okay. Well, it says it returns the distance from the search point to the closest point in the point group. Well, does it? Okay, maybe I have to input some value right here to define which point I am looking for, and this is the point value that I want to look for. But since this is on a primitive value, which doesn't really work, so, and seems like this works on the point attributes. I guess I need to create a point attribute in order to use this. Alright, well then I could get the so this is, I could calculate and near point SPT using near point using this S position. So maybe I can use this one. Let's type this SPT. No, I think I have to. Wait. How? I think I need to convert the integer to string like this. Okay. Now, what else? Do I need a closest point? Not really, but and what's distance metric? What's that? The method to use measure distance. Accepted values are edge and surface. Edge distance is measured along the edge of the model. The surface distance measured along the edge and across single polygons. Surface distance is better approximation of the true geodesic distance. Okay, so then this surface. Right. How does this work? Okay, I have error. Okay, where is the errors? Let me see. No much function for float. Okay, seems like the parameter I input is wrong. Let me check again. Okay, so first one, geometry, should be okay. PT group, that is string. This is should be okay. At p string should be okay. Oh wait, okay, so this was wrong. Search point, this should be integer. The point to measure the distance for right. Distance from the search point to the closest distance in the point group. Okay, then I'm going to convert this into NDI2 or just PT_num. Oh wait, I cannot use that because I'm currently in the point primitive wrangle. Okay, let's get the PT_num equal to near point at P. Wait, not this one, this one. Alright, how's this? Still invalid. Okay, closest PT integer distance matrix. What's wrong with this? Multiple declaration of dist. Oh, so right, you're right. Okay. So this is the result of using a distance calculated using a surface distance instead of a straight linear distance. Now, I do see some changes, I think. Let's compare that. So this was the previous distance function. Let's move this to right here. And this is the one that's new using the new distance function. I mean the surface distance function. So theoretically, or in my imagination, the surface distance hopefully will give you a smoother result, but doesn't really look smooth right here. If I change this to a original distance 1, it seems like it gives you a more smoother result, although the end geometry looks a bit weird. Overall, the overall geometrical shape for using the surface distance looks better, but the detail looks a bit jaggy. Maybe this maybe it is referring to the edge network as well, so that might be the reason. If I okay, surface distance would look much better with the rubber toy, I guess. Okay, let's try that. Okay, so this is the one that with the rubber toy. Let's move the starting point to somewhere around here. Okay, where's that? Okay, right here. Let's also reduce the height, maybe increase the wave. It does indeed looks more like a spiral wave, although I see something not working here, and that I guess is because these faces are not connected together. So maybe the surface distance doesn't work with the surface that is not connected. When it's separated, maybe the surface distance doesn't really work. I'm not really sure, but seems like that's what it's happening right here. Also for those how do I call these? I don't know how to call that. Okay, well, let's try to replace surface dist to dist again to see the difference. Okay, well, the end shape when using the distance that I was using is a bit off because it's just using a linear distance function. Yeah, it's better when using surface dist. Even for the end part looks the spiral wave, how do I say, the width is constant everywhere, so that's great. Okay, well, we can connect them with VDV. That's true, although it makes it more high poly as well, but we could do that. Yes, it's true. VDV, oops, not this one, VDV from polygon, and convert this back to polygon. And I might want to reduce the resolution. Maybe I could just reuse remesh. Well, I guess this works. This should work. Let's set it to somewhere around here. 0.25. Okay. Let's see. Okay. Well, it's a bit too jaggy. Let's set it to 0.2. Still a bit too jaggy, I guess. But I do like that the wave width is constant at any place. That's pretty good. So I mean, to make it more smoother, I can probably use like attribute blur at some point, maybe around here for the height attribute, like this. And oops, not really. Maybe I can use a proximity. Nope. Or okay. I'll right. I think I need to change this one, not the weight. And this does, I am not sure if this works on the primitive. Maybe not. Maybe not. Right. Well, how do I do that? Method, uniform, edge lengths, Laplacian. Can we use smooth? I don't think so. The one that I have calculated height is right here, but that's for each primitive. And to make this smooth for primitive attribute, I'm not really sure how I can do that using attribute blur. Maybe I need to do some I need to remap into point, then remap again to the primitive, or just do the vex operations. Not really sure. Well, I guess the surface distance depends on the smoothness of the surface, or the distribution of the meshes doesn't always give you the smooth results like this. Divide with compute dual can be interesting. Probably, yeah. Let's try that out as well. Indeed, it is interesting. Yeah, I do like it. And now the jagginess doesn't really look obvious anymore. Looks awesome. Looks awesome. Yeah, love it. Thank you. Thank you for the tips. Looks great. What if I change this to old distance again? Maybe that's not gonna give you better results. The overall smoothness become better, but doesn't really give you the constant wave width. So I guess it depends on your needs, but having a constant width is, I guess, it's a good idea in terms of showing the spiral waves. So yeah, I like it. All right, so that was side notes. That's it's not actually inside the hip file that I have uploaded previously, so I can upload the one that I have just done here as a new file in GitHub Git repository, so that you can download this later on to check out the difference between the results, two results. Okay, so oh, and forgot to thank Tokiren for the super chat. Thank you very much. Thank you very much. Okay, so I would like to end the streaming at this point. If you don't have any questions, I would like to end here. In the end, thanks to Sal, I was able to update my file here, and I learned new things about it as well, so always appreciate the new comment. Thank you very much. And so this was for this week. I'm not sure what to do for the next week yet, but I'm planning to do this Algorithmic live next week as well at same time, 9 p.m. Japan time. So if you're interested, if you have some time, I'll be appreciate to have you guys all. Okay, thank you very much, and hope to see you next week. Bye. And I will leave this as an archive so that you all can watch it later on with my struggle. All right, thank you.